coming from University of California, Los Angeles, so UCLA, is Uni. So Uni will talk about TEM-MED bench, which I think is evaluating temporal medical image of VLMs. So a very interesting topic, aligning these VLMs into medical domain. So I'll let you present us this cool work.
Okay, thank you, Paul. Yeah, I'll share my screen. Okay, can you see my screen?
Yes.
Okay, good. I'll get started. So yeah, I'm Junyi, and today I would like to present our recent work on TEM-MED bench evaluating temporal medical image reasoning in vision language models. So our work focused on evaluating the vision language model's ability in medical domain.
Are you sharing your screen? I don't see your screen, or maybe it's
I can see my screen.
Yeah. Okay. Yeah, I can see your screen. Sorry about that.
Okay. Okay. Our work focused on evaluating the medical vision language model's ability in medical domain. And so the task is we have a medical image as input, and the output would be natural language output. And in this field, existing benchmark mostly focus on analyzing a single image, and that image is from a single visit of a patient. And but obviously, this kind of setting deviates significantly from the real-world clinical practice, since in real world we know that when a doctor want to analyze a patient condition, they will not only need to depend on the medical image from that specific visit, they need to also consider the historical condition of that patient. So our benchmark is built to bridge this gap. In our benchmark, we have two images in each data. The first image is from the current visit of a patient, and the second image is from the most recent historical image of the same patient. And our question is focused on analyzing the condition change between these two visits. So our benchmark has multiple image as input, and our question focuses on the temporal reasoning ability for vision language models. Yeah, and in our benchmark, we have designed 3 types of tasks in order to give a comprehensive evaluation for existing LVMs. And for the experimental size, we did experiments on 12 LVMs, and we not only did our experiments in closed book setting, we also did our evaluation in open book setting. And and we released knowledge crops of more than 17,000 data. Yeah, and this slide is the overview of our benchmark to give you a high-level understanding of what we have done. And next, I will go into the details of the benchmark's construction and the related experiments. So our benchmark is built upon a key observation of existing medical report generation dataset. We found that while this dataset typically assign each report to a single visit, after broadly observing this report, we found that actually some reports include sentences that describe changes in patient's condition rather than just the condition at that visit. For example, in this report, it contains a lot of keywords that used to describe changes in patient condition. So obviously, this kind of report, when the doctor writes these kind of reports, they definitely not only depend on a single visit, they have also considered historical visits when writing this kind of report. So based on this observation, we picked a set of keywords that used to describe condition change. And we picked the report from the CheckPlus dataset, in which each sentence is a condition change description sentence. For example, in this report, each sentence is used to describe a change in patient condition. So we picked this kind of report as our raw data. And for this kind of report, although there are 2 sentences used to describe contingent change, but the other two sentences is not a contingent change description sentence, so we didn't select this kind of report. And in this way, we can guarantee that the report in our data is purely used to describe the change between two visits. So after selecting this report, we use metadata in the check squared plus dataset to track the most recent visits of the same patient, and pick the image from that visit as our last visit image. And in this way, from the 220K report, we can pick 18K report as our raw data. And we split this part of report into two parts. We use 17,000 data as a knowledge corpus, which is used to do retrieval or training. And we picked 1,000 data to build our test set. And we further convert this part of data into three tasks: VQA, report generation, and the image pair section. Yeah, and it was noted that for the image pair section task, this task is relatively new compared to previous work. In this task, we have a medical statement in the question, and we have three options. Each option is a image pair, and we let the model to select which image pair best matches the medical statement in the question. As you can see, this kind of task require the model to have a high multi-image processing ability. Yeah, and next I will introduce how do we convert our test set into these three formats. For the report generation task, we don't need to do actual works because the raw data is already in the report generation format. And for the VQA task, we first split the report into sentences. And for each sentences can be rephrased into a question that targets a contingent change. For example, if the original sentence is the long values are decreased, we can rephrase this sentence into a QA pair. Are the long values decreased on the medical image with the answer yes? And another example, if the original sentence is increased right bacillus obfuscation, the QA pairs would be has the right bacillus obfuscation decreased, and the answer is no. And to balance the distribution of the two classes, we let half of the data with answer yes and half of data with answer no. Yeah, and because we prompt VLM to do this referencing process, after we using VLM to do this process, we applied a manual check to guarantee that the QA pairs is aligned with the ground truth in the original report. Okay, this is how we build our VQA task. And for the image pair section task, after broadly observing the report in the dataset, we found that most medical statement follows this kind of regular expression. So the medical statement start with some contingent change keyword with several attributes and end with some possibility keyword. And in this way, we select a set of keywords that used to describe change in patient condition, and then we select a set of pathology that occur in our raw data, and we use this kind of regular expression to assign medical statement label to each report. And when building the data in image pair section task, the most important thing is to guarantee that the medical statement in the incorrect options is not the same as the medical statement in the correct option. So in this way, if the correct option contains a medical statement, increase the consultation, the incorrect option should be selected from the set with the medical statement label unchanged consultation or persistent consultation. And in this way, we can guarantee that only one option matches the medical statements in our question. So this is how we built the image pair session task. Yeah, and for the quality control, we would like to say that our data construction pipeline is deliberately designed to minimize the need for additional expert relabeling while still maintain high canonical fidelity. Actually, in our, as you can see, in our data construction process, we intentionally avoid relying heavily on LLMs to synthesize new data. In contrast, we focus on identifying potential patterns in these highly standard reports. So for the report generation task, one way to build this task is that we can just pick two adjacent reports and we prompt LLM to generate a condition change report based on this report. And so we can get a lot more data. But we didn't adopt this way because if we prompt LLM to analyze the condition change based on the two reports, we need to apply expert verification of the reliability of the report. So for the report generation task, we directly select the report from the checked plus dataset in which every sentence is a condition change discriminant sentence without generating new clinical findings. And since this report is directly selected from the original dataset, we can guarantee the faithfulness of this report. And for the victory task, we prompt LLM to perform a purely syntactic transformation from the original sentence to a question and keeping the underlying clinical statement unchanged. And this kind of option do not require any medical statement beyond preserving the meaning of the original sentence. And since we adopt LLM to do this perturbation, we further applied a human review to ensure that the answer is consistent with the corresponding sentences in the original report. And for the image pair selection task, we design a regular expression pattern over a fixed set of contingent change keywords and pathology terms. And this regular expression is tailored to the highly standard wording of the radiology reports. And yeah, when we design this regular expression, we apply a manual review around 100 reports extracted by our pattern and confirm that all of them contains the intended target report target condition change. And we use regular expression in order to guarantee the high precision of our classification of condition change rather than the high recall. Yeah, and I would like to say that there might be some data that has similar condition change missed, but that just influence the data amount rather than the data quality. So this is the quality control part. And as I mentioned before, we not only did an closed book evaluation, but also did an open book evaluation. So for the retrieval augmented generation used in our evaluation, previous reg method in the medical domain mostly focus on text-only reg, which means they use a medical image to retrieve a report, and they use this report as additional information to help the model answer the question. And in our work, we further explored the utilizing of multimodal reg in the medical domain, in which we use the medical image to retrieve an image plus report pair, and use the image plus report pair as additional information to help the model answer the question. Yeah, and for the retrieval method used in our work, previous work mostly just using the image, either use image to retrieve a similar report or use the image to retrieve a similar image and find the corresponding report. But in our setting, since we have two medical images in each data, one from the current visit, another from the historical visit. So we first compute the similarity between the historical images, then we compute the similarity between the current visit images, and we add them together. And this kind of retrieval method can guarantee that the condition chains are similar. Yeah, and here is our experimental result. We did experiments on 12 LVMs with 6 proprietary LVMs and 6 open source LVMs. This is the evaluation result in closed book setting. Based on the evaluation result, first we can see that our benchmark is extremely challenging for existing LVMs on the weekly task, except for Cloud 3.5 Sonnet and GPT-04 Mini. Other models just reaches at a random guessing level because for the weekly task, our weekly task follows a 2-option setting, so the random guess level is 50% accuracy. And for the report generation task, all of the models reaches a very low score. And for the image pair selection task, in this task, we have 3 options. So the random guess level is 33%. And all of the models just reaches at a random guess level. And when you compare the medical LVMs with open domain, with general domain LVMs, you will see that actually medical LVM do not perform better compared to general domain models. And findings reflect the lack of robustness and generalizability of current medical LVMs, because actually for these LVMs, they just fine-tuned in a single weight image setting, which means in their fine-tuning data, they also have 1 images and and with some neutral language output. So another reason might be that current medical knowledge fine-tuning scheme often erode the bodily reasoning ability inherited from the general domain pre-training, and this makes the medical LVMs do not perform better than general domain LVMs. And when we compare the proprietary LVMs with the open source LVMs, we can see that actually proprietary LVMs consistently achieves the best performance across all of our 3 tasks. Yeah, and this indicates that the advanced image reasoning is critical in our benchmark. And then we did a further evaluation for our benchmark in the open book setting. And we compared the text-only RAG with multimodal RAG in the medical domain. And we found that in our benchmark, the multimodal RAG performs better than text-only RAG across most models in most settings. Yeah, and I would like to. It was noted that for the image pair selection tasks, actually the multimodal RAG do not perform very well, and we think it is because in this task we have 3 options and we have 6 medical images as input. If we add and retrieval data, the model needs to align the retrieved information with 3 separate pairs, and this splitting its attention and amplify the retrieved noise. And this underscores the need for advanced methods to improve LVM's ability to utilize the retrieved multimodal information. Yeah, and here's some additional experiments. This is a Bayesian study on our retrieval method. We found that our pairwise image retrieval achieves the best performance. And this is experiments on top 1 to top 5 RAG. And we found that the multimodal RAG consistently outperforms the text-only RAG across top 1 to top 5 RAG. Okay, here's some additional experiments. we further analyze the 3 of the latest SOTA priority models on our benchmark, which is Gemini 2.5 Pro, Cloud Sonnet 4.5, and GPT 5.1. And we found that even these priority LLMs do not perform well on our benchmark, and this shows the long-term difficulty of our benchmark. And this experiment is used to investigate whether there's a potential inflation of real gains in our open book evaluation. In this experiment, we further evaluate the model performance in these 2 settings. One is that we allowed the image from the same patient in the retrieval pool. Another is that we exclude the images from the same patients in the retrieval pool. And we found that the model performance in the same patient exclude this setting is nearly the same as the same patient allowed this setting. And and this result indicates that allowing same patient retrieval do not inflate the real gains in our evaluation. We think that a key reason is that TenMed bench focused on contingent change rather than the single wave pattern matching. Even if the retrieved image pair comes from the same patient and the absolute conditions of these images are likely to be similar, the contingent chains are not guaranteed to be similar. And these experiments enhance the reliability of our open book evaluation results. Okay, and I think that's all for my presentation. Thank you. Thank you.
Thank you for the talk. So I guess we have about 6 minutes for questions and discussion. Does anyone have any question? So I think there are some people in the audience. If you have any questions, you can also post it with Q&A button on Zoom, or you can also post questions on Slack. In the meantime, I have some questions as well. So I see that you're doing a multimodal RAG, which is kind of an interesting concept. And there are 2 parts of it, right? So one is retrieval and the other one is generation. Can you clarify which one of the 2 or both of them where you're using multimodal data, text and image?
Yes, in the text only RAG, we just retrieve a report and add that into the prompt to help the model answer the question. And for the multimodal RAG, we use both image and the report and add that into the prompt to help the model generate the answer. Yeah.
And for retrieval, I think you said you're just using the input image to do the retrieval. Is that right?
Yes, we use the input image, yes.
Because there's no text linked to it. Okay.
Because in our data, when we prompt the model to answer the question, we only have the image as the information to do the retrieval. We do not have text information to do the retrieval.
Yeah. Makes sense. Another question. So I've seen a lot of results in the slides, including the result where you say Gemini 2.5, I think, was actually very good, and all the open source models are rather similar to each other. How do you explain the gap in performance? Where is that coming from? Is that more about medical knowledge these models may have, or is it more about, I don't know, visual recognition capabilities, or can you break down the score difference here?
I think the most important reason for this gap is the multi-image processing ability. Because first, for the 3 medical LLMs we evaluated, these 3 medical LLMs are just fine-tuned in a single image input setting. So for this, if we just apply these three medical LVMs into our benchmark is either have at least have two medical images as input. So these medical LVMs may not appropriate to directly evaluate in our benchmark. Yeah, because since they only fine-tuned in our one image input setting. And for the open domain LVMs, I think the performance gap between the open domain LVMs with the priority LVMs is just due to the bodily reasoning ability. Since our question is all about the contingent chains, and the model need to analyze two images and finding the difference between these two images. Yeah, and this requires a high bodily reasoning ability for the LMs, and obviously priority LMs has a higher have higher this kind of ability. So I think this would be the main reason why priority LLMs performs better than other models.
Okay, makes sense. Unless there's another question, I have my final question as well, which is
I may have one also, kind of related. Like, what do you think is the gap to improve for even when you show the most recent models? Like, what do you think they lack to have even better performance?
Yes, for the SOTA priority models, they actually also didn't do well on our benchmark. Yeah, and I think first for the weekly task, I think the only reason is that in medical domain, when we need to analyze the difference between two images, the pattern might be very the different pattern might be very slight, and it's hard for the model to analyze the difference between these two images, and this might just due to the inherent medical ability for these two models. And for the report generation task, I think apart from the reason I mentioned before, another reason is that this kind of open form output is very hard for existing models, because actually in this report there are a lot of this kind of report follows a very strictly or standard wording format, and the model need to first learn how to generate report in this kind of wording, and only if they know how to generate the report in the wording aligned with the clinical domain, they can get a high score. And I think that might be one reason why this SOTA model still not performs good on report generation task. And for the image pair selection task, I think the most important reason is multi-image processing ability. Since actually I found that even for the SOTA LVMs, they are not able to process images with a number higher than 5. So, and in our setting, we have at least 6 images input. So the multi-imaging processing ability is critical, and has a very and has improvement room for existing models. Yeah.
Okay, thank you. Okay.
Thank you.
So now you switch, right?
Okay. Yeah. So it's my pleasure to introduce Paul, our second speaker, Paul from EPFL, to present his paper. And I think his paper is titled "Towards Smaller Visual Document Retrievers." Yeah, and it's in the retrieval augmented generation setting, I think. And I'm also very interested in this field. So Paul, please go ahead.
Okay, so thank you very much. So exactly, it's interesting that your paper had a clear part on actually on retrieving and retrieval augmented generation. So can you see my screen now?
Yeah.
Yeah.
Maybe I can do better. Yeah. Well, you'll see the top bar. Sorry, I don't know how to hide it, but anyways. So yeah, exactly. So I'm gonna actually go deeper on the retrieval part in my talk. So we're gonna talk about retrieval and especially visual document retrievers, which are a really powerful tool to equip for LLM and agent to answer typical questions such as medical one as Uni just presented. And so I'm going to present the work I did at Living Technology recently, where we trained a modern VBERT, which is a model where we try to get towards smaller and more efficient visual document retrieval. So let's start first with a quick recap on what is document retrieval and why is it useful. So first of all, like why are retriever important and why should we take care about it is for RAG, obviously. You first introduced this, but let's quickly recap. So RAG can be described through the schema. So basically, instead of having the user directly question the LLM, you will have first a retrieval part where you get some relevant context from a structured database of your documents or whatever data you have, and you add it to the context. So after the query, you have your context and pass it to the LLM to give an answer. So for example, if my DB is Wikipedia pages and my question is, where was born Napoleon? I would expect my retriever to get a passage of the Wikipedia page that answers the query, such as like a paragraph where it talks about where it was born. And so yeah, this is a pretty popular framework. And why do we care specifically about documents? So PDFs, well, because they contain most information. Basically, whether it's online data, you can see any website as a PDF. You can convert most of it. Like academic papers are like really important source of information, but even private ones for a company. Many reports contain all the information you need for any source QA. So this is why you want to focus on documents and have a method that it really adapted to this type of source. And so why is the framework of RAG really interesting and really used across many fields is that it is really effective because of the ability to refine the LLM knowledge. So why is it so appealing is that, in fact, you can basically by providing relevant context, you can control your source. So if you're not sure that the LLM can answer your question without having this source, well, in fact, you can achieve better fulfillment. So if I have, my goal is to create a chatbot that answer question on some guidelines of my company, well, the rack setting is perfect because without really fine tuning the model, I can actually like control the output and ensure that it source given my context. So since document retrieval is powering the RAG, you can pretty much ensure that document retrieval is actually key for any source QA. And so having this in mind, now that we know that why retrieval are important, because it powers RAG pipeline, maybe we can ask ourselves, so, okay, why do we need more efficient document retrievers? And so first, I'll quickly introduce like historical methods, and then we'll come up with why we need more efficient ones. So first of all, like historically, what was done is that this method of document retrievers were relying on a huge pipeline, enormous pipeline, where first you had your page that you will OCR, then you will run layout detection to extract the paragraph and the image, then you would caption the image, you would chunk your text, then embed it, etc., which is really long. And each step can ensure, like, can introduce error actually. So in fact, you would have a process that is slow, noisy in the end. You don't have precise chunks in your database. Actually, like from the Colpally paper, they ran an experiment and they seen that an average pipeline could take around 7 seconds per page, which is huge. If you imagine that you have 100,000 PDF of 100 pages, like you can compute the time. It's really, really long. And you don't want this, obviously. Also, the performance we'll discuss later, but is quite capped because of all these steps, as I mentioned. So recently, what happened is that people came out with a new idea, which is called visual document retrieval. And so instead of operating at the text level, why not directly working on the page screenshot using VLMs? So you have now VLMs that are really good multimodal understanding, as shown in Yoni's work, an example. And so, well, why would you bother to use complex pipelines if you can just embed the page? So that is the whole idea about visual document retrieval. And one of the main work on this is ColPaly, and ColPaly combines this idea with multi-vector matching. So I'll define this later to capture fine-grained information in document pages. This leads to huge performance improvement and faster indexing. So in fact, like you come up with an average encoding per page of less than 0.4 seconds, sorry, which is enormous gap and huge improvement from 0.66 to 0.8 in the CG and video array. We'll discuss later about it. So yeah, basically VDR combined with fine-grained matching gives enormous performance gains, and this is the current state of the art. So yeah, here you can see. So here is an example of why it works, how this works. So basically, so the idea is that you match each token with some visual cues on the document, and this is what makes this technique really powerful. So an example here for the query, which hour of the day had the highest overall electricity generation in 2019. Each token will be matched with a part of each document. And so in example here, you can see the visual cues that the VLM would look at for the token hour. And you see that it's quite actually relevant. It looks at the hours, the different hours on the graph, and gets some visual cues. So that is really interesting. And this would probably fail, or at least like you would have errors in big text-based pipelines. And so now, basically, what's the problem with VDR? Why do we work on this? Well, they are built on VLMs. So these VDRs, basically, you take VLMs and you repurpose them to have visual retrievers. And so, well, basically, we don't really know if it's the correct way to go to start from VLM to have an encoder. So the main intuition behind this is that VLM employs causal attention, and that there have been work on the text space that shows that very bidirectional attention is actually better than causal attention for information retrieval. So you can have pretty strong feeling that this VDR might be suboptimal for the moment. And so an example to illustrate this would be the following query, where it says which bat is used in baseball. Actually, like in bidirectional attention, like your query, like the token bat would be correctly contextualized because it can attend to baseball. So actually, like this queried bat, when it will match to the document, it will be precisely describing a bat in the context of baseball. Whereas in causal attention, the bat token only attends to which might lead to huge noise because it can match to some bats, animals, documents, and therefore introduce noise in the scoring. So yeah, there are many problems with VLMs. Most one is that they're getting bigger and bigger. So this is also a limitation, as you want your retrieval to be fast and work, if possible, on CPU during inference. So all of this brought us to a question of how can we get towards better visual document retrieval. And so we've been thinking about this with the colleagues at Ilwin, and we're like, okay, maybe we should give it a try and start from the beginning and say, okay, if we were about to train a VDR, what should we do and where should we start? And so after discussing all this, obviously, like the first question that comes in mind is like, what should be our backbone model? So VLM uses decoders as their backbone model. As we said before, there is a strong feeling that this might not be optimal. And so first question is like, what about using directly an encoder such as a BERT as the VDR backbone? And so to really understand this, maybe I can explain a bit how VLM works. So these VLM are using the early fusion architecture where you take a pre-trained VLM, you add it a vision tower, which here is cyclic, and therefore you have a fully functioning VLM. So you take this gamma model, which is pre-trained, you add this vision tower, you train it such that you train a linear projection such that the language model understand what gets out from the vision model, and that way you have now your language model that can understand image and answer a question. And so in our first question, we want to understand, okay, what if instead of this transformer decoder, we would have an encoder? And so we designed a simple experiment to understand like what is the advantage of this architecture in general, of having like a pretext language model in which we add parameters to understand the vision, and also what if we use an encoder? And so to do so, we train two generalistic visual retrievers, one which is based on an encoder, another one on the decoder, and we compare them on various retrieval tasks, not only focused on documental, but generalistic tasks. We train them on single vector mode. I'll come after about the multi-vector mode. So we have a single representation for each query and each document. And so the model are trained on exactly the same data, only different on the attention scheme. And for the first phase, where we train this linear projection, we use the Cauldron, which is the pre-training data set of small VLM. And for the post-training, where from this VLM we create the VDR, we use VDORE, which is a standard, like really famous documental retrieval data set introduced in Copali, and MS-COCO, which is the really famous data set about image and natural image and captions. And so we compare these models on three main categories. First one is document retrieval, then is image caption retrieval, and this one is image classification. And so we compare these models to their vision backbone alone, because, okay, well, what if only using the SIGLIP was better than having to bother with the full VLM? And the results are as follow. So what does it tell us? First, interestingly, like there is a huge difference between anything that is documental or non-documental. We see on the left that basically our small ablation models beat their SIGLIP baselines, actually significantly, because it even beat the larger version of SIGLIP for the encoder. Whereas on the other tasks, which are based on natural images, like non-documental images, there is a huge gap between this early vision model and the vision backbone alone. And so basically we can draw a simple conclusion here, is that this early vision architecture helps for document retrieval. So basically, like, these VDRs are in the right path, in the sense that this is the way probably to go to add some textual parameters to a vision tower, because it helps it helps on the document retrieval. Now, another thing that we see is that the encoder counterpart slightly outperform the decoder counterpart. So we have maybe a slight idea that this might work better, but it is still unclear, and we want to dig a little bit more into what's happening. So what we do is that we try to analyze the training dynamics. And so for each multiple stage of the training, basically, we train a VDR. So basically we take our modality alignment and we post-train model at different steps. And so that way we have basically VDRs at different step of the pre-training, and we analyze the performance to see kind of scaling dynamics of these models. And so on the natural image task, we obviously see that it's hard, and probably like that this type of model would never catch up, even if you would give it more tokens. But the interesting part is rather on the documental part. So you see that actually for encoder models, it's scaling quite well. There's some evidence that probably if you let the model train longer, it will still get better performance, although it's not sure, but there's at least good signs. And also, comparing to the decoder model, it seems that the decoder is better in sampling efficiency, in the sense that it reaches its top performance quite quickly, but then plateaus compared to the encoder. And so that says that we should probably scale our data if we go on an encoder model. Now, there's a thing that we still need to explore. As I said before, like, okay, encoders seems like better than decoder in single vector mode, but as you remember in the beginning, I was mentioning that Copali is based on fine-grained token level matching, which is this late interaction matching. And so what we want to do is that we want to continue this comparison between decoder and encoder we are doing, but this time at fine-grained interaction matching level. So we'll use the late interaction matching, in opposition to the dual encoder. So basically the way late interaction works is that you have token-token comparison. So for each query, basically, for a query document pair, for each token of the query, you will match it to the most similar token of the document. And that way, basically, you have more fine grain. Like basically, if you have some tokens that are precisely matching some of the document, you can capture this. Whereas in the single representation schema, you would compress all the information into a single vector, and therefore you can lose some nuances. And so next up, like we do the same comparison we've been doing in the document retrieval setting, but this time using multi-vector matching. And so we compare the performance of our two backbones, as always, our two settings. So decoder and encoder on Vidore, which is documental benchmark. And so we still have our encoder, our decoder. We have other baselines, which are basically kind of in the middle of encoder and decoder, which is taking a decoder and training it with mask language modeling, or decoder and annealing it at encoder. And we compare single vector and multi-vector. And here are the results. And actually, quite interesting results because this completely highlights the need for an encoder model. In fact, we see that in single vector, there is no clear difference, because if you see the dark blue bars, actually, like, it's hard to tell which one is the best. Okay, encoder is maybe slightly better than decoder or the other, but nothing clear. Whereas if you see the multi-vector approach, there is a huge, significant gap between encoder and decoder backbone. And in our intuition, that makes a lot of sense, because when you think about the late interaction matching, you need to have all of these tokens really correctly contextualized, because they will all contribute to your score. And if you think about the example I was giving in the beginning about the bats, if your token bat is not correctly contextualized, it will bring noise into your late interaction scoring. And so this result completely highlights this and tells us that if we want to go for a multi-vector matching on documental, we should probably go for an encoder backbone. And so on this small comparison on the famous Yama for the decoder and the bird for the decoder, we can see that if we want to build a visual document retriever from scratch, we should probably start from an encoder backbone. And so collecting all this great high insight that we had from our experiment, we said, okay, maybe we can now start to think about building a model. There might be room to improve over the current VDR. And so we go for training a new model, which called modern VBERT, because it is based on a modern BERT architecture. We'll discuss this later. And trying to build a small yet mighty video document retriever. And we have still quite a question to answer. Basically, like scaling up, like we've been discussing that probably we need to throw in more data. It's hard to do more on the pre-training part because data is hard to get. And obviously, given the scale, like we could contribute much more than what's happening. But on the post-training side, which is starting from the VLM to train the VDR, we can do stuff actually, because okay, maybe we lack of query document pair at some point on documental setting. But in fact, exists a huge set of data set that operates at the text-only level. And maybe we can use it to mix it with image text data sets and to improve performance. And so we run a quick and simple experiment where we vary the text-image ratio. So basically, we take Vidore, which is query document pair, and RLHN, which is a text-text retrieval dataset. And we just add more and more of this RLHN into the dataset and see how the performance evolves. And so again, we evaluate on documental retrieval, which is Vidore. And here are the results. And this is clear that, in fact, adding this text-only model the data is beneficial for visual document retrieval. And this is a good news because we have a ton of them. And that way we can extend our contrastive pairs sets. So in the end, we end up with the following contrastive set. So we take the Kolpali data set, which is query document images for visual retrieval. We tested other query document because there is plenty of them. The problem is that we didn't see much improvement, probably because they draw all from similar distribution, whereas where we were adding chain, here we were gaining a lot of performance. So this is our final contrastive pairs. So it is roughly a little bit more than 1 million pairs. So this is how it is. And for the modality environment, which is starting from the encoder, going through our vision language model. As I said, that there is not much to do more than what's happening. So we'll take again like the small VLM pre-training dataset. And on this, I want to thank the small VLM team and Andy for providing us with the mix and helping setting up the data, which can be painful because of the size. And so basically the Cauldron plus or Cauldron 2, whatever its name, is just a general mixture of knowledge and visual understanding to pre-train some VLMs. In our case, we use it to start from modern birds to create modern V-birds. And so, yeah, here is basically the recipe. We take strong backbones. So our encoder language model would be 18, 150 million parameters, which is basically an evolution of modern V-bird. It is the same architecture, made by Antoine Chaffin and its team at Titan. And for the Vision Tower, we'll be keeping our Siglib2 baseline Vision Tower because it is a really strong Vision Tower, and we'll scale on the data, adding more modality alignment tokens, sampling from the same data set, scaling the contrastive pairs, as I mentioned before, with some text-only data, and plenty of other way that we scale that are described in the paper. Notably, we did some experiment on the resolution of the image, on the use of synthetic data. But for the simplicity of this presentation, I will skip this, but I encourage you to have a read because it's quite interesting on the details if you want to train a VDR or even a VLM by yourself. And so we launch the training, we take a bunch of GPUs, we wait a bit, and here are the results. So in the end, we end up with a modern V-bird with 2 variants, multi-vector and single vector model that achieve performance of models 10x its size, which is huge. So you can see that, in fact, the multi-vector so-called modern V-bird is matching Kolpali on a documental task, while it is 10 times less big model. Same for a single vector model, quite interesting performances. It largely beats its Vision Tower baseline. It almost reaches Colfro, which is a model of roughly its size, while Colfro is multi-vector, so quite encouraging. But yeah, the main, I'd say, achievement remains called modern V-bird, which has really interesting efficiency instead of the model size comparing to its performance. And we want to go further because having efficiency in model size is nice, but the really interesting thing that we want for retrievers is to be able to run it fast, because when people are running queries, you want them to be processed fast, because if you have to wait a long time to get the answer, if you add to the fact that an LLM answer can be slow, then it starts to make a lot. Also, you want it to run on CPU, which is not necessarily the case. The latest VDR models that are quite on large QAN models, in fact, are hard to make run on CPUs. And obviously, not everybody has access to CPUs. To GPUs all the time, sorry. So it's better if you make them run with CPUs. And so we measure the online efficiency of modern V-bird, which means like we measure like the time it takes to process queries with modern V-bird. And so we get the following results. And so this table shows the performance of the VDR split by VDR V1 and V2, only for the English split, and the latency. So basically what you see is that, okay, yes, it reaches the performance of Kolpali in term, like with 10x less parameters, but also it is almost 10x times faster for processing queries. So this is truly what's really interesting for the practitioners, because modern VBERT is not only a small model, it's a model that is fast at query processing and works on CPU. So even some work from the guys at Vespa, leading by Thomas Thorsen, has shown that with Onyx quantization, you can even get better performance from cold modern VBERT, which is really encouraging. And so, a lot being wrapped up, we try to build a model that is faster and at least like more adapted to everyone usage. And so the idea was that to have basically efficient video model for everyone, and because reaching this is crucial for a lot of real use cases, because obviously not everyone has access to GPUs. And so I think that there is plenty of work to do towards this direction. In fact, you can say that document retrieval is not solved yet. There is plenty of challenges. Query latency is obviously better with modern VBERT, but like it's still slow. We can do better. Like if you think of the problem, it is asymmetrical, so we can probably come up with even faster solution. Indexing latency remains slow because processing image is slow with this type of model because it has to get multiple for passing to the SIGLIP. There is still a question on the multilingual performance, how to contextualize documents, which is some direction that Max Conti, which is a colleague from Edwin, has been exploring. How do you integrate it into agentic RAG is also a really interesting avenue. Basically, there is still a lot of work to do. We are not reaching the optimal VDRs, whereas it is truly important for most of our pipelines of AI pipelines today. And so with this, I reached the end of my point. I want to thank you all for listening. Here's a QR code toward the HF page with all the information about the model, the paper, the GitHub, whatever. If you have any question, you can ask them to me or any of the authors. And yeah, thank you.
Thank you. So it seems that we have one question from the audience, and I just allowed Mayank to talk. So if you like, you can also just step forward and verbalize the question.
Sure. So like I was referring to your like the speed and the latency. So I had put in the question in the Q&A where I have uh, written that when scaling to 2048 pix, the sequence length grows significantly. Modern BERT handles 8K tokens efficiently, but the SIGLIP, the Vision Tower, processes fixed 512 pix tiles. So in your highest res cooldown, is the performance gain coming from the model actually resolving fine-grained visual details like small font text, or is it simply that the increased number of tiles provides a form of data augmentation or like via overlapping crops? And my second in the like the subsequent query will be, did you visualize attention maps to confirm the model is attending to features that were invisible at 1024 pix?
Okay, so thank you very much. That's actually a really good question. So I think there's two parts. First, I'll answer at the first one, which was, if correct me if I understand correct, do we think that increasing the resolution is leading better performance because we have basically data augmentation in the sense that we have crop that are overlapping, or is it because it handles to read like font that might be small? Is it like your first part of the
Yeah,
question?
you regressed there for a bit, but like yeah, in the Q&A panel, if you go to the Zoom's Q&A panel in the bottom bar, I have written the question there.
Uh, I don't know if we can see the Zoom since I'm sharing my screen. But yeah, I'll try to answer.
Yeah.
I think I get your question. Basically, I think that's the experiment we ran is kind of to confirm what's happening. The cooldown was rather to get like an idea of getting better performance without extending the training. So this is kind of a common idea that having larger resolution leads to better performance. And in fact, like it's from the literature, it's because like it allows the model to capture like basically having more information per token. So basically, like each token will represent like a smaller subtrot. And so because like each token, like if you have too much information into one token, maybe you will compress it. So that's what make the powerful like combination with the late interaction. So I would say that it's because you have better expressivity in each of your token by increasing the resolution. And so this is important in documental stuff because it allows the model to get all the first of all the words that are there, but also like understand like the layouts in more details. And for the second part about visualizing the attention maps, we did some after the publishing the paper, we did some check on the attention maps. In fact, it is quite interesting. So I have to mention that it's hard to visualize with this type of model because let me go back on the slide because they have pixel shuffling and yeah. So basically you see here there's pixel shuffling and this operation kind of like compresses multiple visual tokens into themselves. So when you visualize the attention maps, it's not as clean as it was in the Colpani paper, but still, like you see that it is like attending to the correct part of the document. Sometimes it fails. I think probably because it's mainly on complex layouts such as graphs and everything, and I think it's more related to the encoder element. Because in the end, this Siglip tower is kind of used by many other models. So you can say that this is not the difference from our models. But yeah, definitely there is room to on improvement on where it visualizes. And I think it would come from a better backbone first, and second, better data. But really good question.
Yeah, and my like second question will be since small models traditionally struggle with the complex reasoning, so if a user asks a question requiring a synthesis of a visual data, like compare the trend in the top left chart with the table in the bottom right, so does the 250 parameter like 250 million parameter capacity limit the model to a fuzzy OCR matching, or like you evaluate the model based on the tasks that require multi-hop visual reasoning?
Well, the thing is that this model won't answer a question. So for a question like draw a difference between the top left image and the right image, then I think it's not really related to retrieval, in fact, because this is not really a query like what is my result from quarter three, because then you can actually like match to a document that is talking about the results in quarter three. But about the fact that this model, like this set of parameters is enough, I think that actually like a good question. I think no, like you have definitely limitation with small models because obviously like larger model or more reasoning. I think you just want to strike a balance where you will know that you cannot match these models with small models, but like the question is rather like, do you need that much performance in your real use case? So yeah, definitely there is a balance. Of course, really, if really small model could reach the same performance as really large, like I think everybody would go for really small. But it's more a question of do I need like where is my bar for my documents and my type of queries? Yeah. Does
Cool,
it answer
thanks.
your question?
Yeah. In a sense, yes. Thanks.
Okay, thank you very much.
So thank you, everyone. The time is up, actually. You can feel free to stay and do more discussion because there's no further session today. But for the sake of kind of wrapping up, I would say we finished the recording here, basically. And well, basically saying we do the editing until this point. Of course, you can continue afterwards. But before doing that, I wish to thank the speakers again for great talks and very informative and very thought-inspiring discussions afterwards. The videos will be online on YouTube in a week or so. We'll let you know when that happens. Yeah, so I wish to thank the speakers and the audiences today, making the great session, especially Mayank, as well as Junie and Paul for coming. So thank you again.
Thank you.
See you again.
Thank you.
Feel free to
Thank you,
stay if you
everyone.
wish.
Yep.
I can also stay a bit longer if you want.
Yeah.
Any questions or?
If you want, I had this fun slide to share quickly.
Should that be also recorded and put on YouTube?
No. It was like,
Not suitable
I was
for.
about to discuss, wait, isn't RAG dead? And so that's something that I feel interesting. I'd love to hear from you guys. You see on Twitter a lot of people like comparing like the fact that you have long context models, and that maybe you don't need RAG anymore. I think personally, like having long context model is not the solution because attention in RAM is so expensive and slow, and like long context processing long context PDF is not, I think, the best way. And especially like, what about if you have 10K PDFs? But yeah, I want to hear from you. Like, what do you think about this? Like, why are people putting that much comparison between RAG and long context?
So if I may, I'm also kind of focusing on this problem nowadays. And I tend to believe something in between the long context and RAG should be a good way to go, where I see a lot of memory networks coming up these days. I think it's a buzzword as well. Where you try to, like, there are different spectrums, right? So when you have RAG, then you have non-parametric system for kind of taking some knowledge from some database, which is totally non-parametric, and you just take that knowledge into context as appropriate. On the other hand, you have this full long context thing where all the knowledge is in context, either in context or in parameter as well. And I think memory networks nowadays are kind of trying to take the best of both worlds in a sense, by trying to sometimes trying to make the architecture a little bit different in a way that you don't really need to have this long context. You can have more hierarchical structures, or have some sort of memory structure, as in like ChatGPT models, where you control what has to be memorized in context. It's almost like orchestration, kind of engineering as well. So yeah, I think the space is vast here, and it should be explored a lot more in the coming years. Like this year, maybe that should be the one of the main topics that people will look into.
Yeah, I agree. Yeah, I agree on the part that there's something in between. Like, it's having long context will help definitely on providing longer context. But then like there is still a question on how you retrieve this context, or how do you build it, like context engineering, kind of. So yeah, that was interesting. I found this screenshot from someone trying to run the long context benchmark.
See.
Where basically he said like, yeah, out of memory. Yeah, that was interesting. I think RAG is still alive.